Teams meeting.
Yep, we can see everything.
Oh,
now.
perfect. All right, let's move before team starts to quit again. Yeah, just let me know when to start, and I'll be happy to.
Sure, that's it.
Okay, I'm gonna go in.
Do you want to put those bar on the side or? Yeah.
There we go.
Perfect. Yeah.
There we are, set.
Okay, good.
I'll go and monitor from the spot.
Okay, and then is it okay with you? We record that and we put on our website.
Sure, not a problem.
So then, okay, if that's the case, darling, are you? Oh, okay, Arlene is not there. So let me see that.
Yeah, Janine is recording, Saeed. I can see the record button. And
Yeah.
I would suggest we ask this question ahead of time, so we don't put the speakers on the spot in the seminar.
No, actually, actually, in email I asked him, but I just wanted to double check.
Oh, okay, sure. Yeah,
So
thank you, Saeed.
Because later on, maybe they prepared their slides, so I just double check that maybe they added something. Okay, so then, okay, so if it is recording, so then we can start. So
okay,
yeah, so, great. Okay, thank you. So today we are glad to have Dr. Venkat Banunarayaanan from the NRECA. So Dr. Venkat is the Vice President of Integrated Circuit and Integrated Grid and at Business and Technology Strategies at National Rural Electric Cooperative Association. He has 25 years of experience in leading and executing energy-related projects involving power system analysis, data analytics, grid optimization, renewables integration, techno-economic feasibility, and benefit cost studies. At NRECA, Dr. Venkat, his role is to lead the development of tools, resources, and partnerships for member cooperative to successfully evaluate opportunities for distribution grid optimization and value extraction, enabling reliable and cost-effective grid optimization operation with high penetration of distributed energy. Dr. Venkat holds a doctorate in electrical engineering and an MBA in finance, and he is certified as project management professional and has worked previously at the United States Department of Energy, ICF International, and General Electric in their energy division. As you see, that Dr. Venkat has ample of experience in operation of power grid, and we are glad to have him, and I'm sure today we learn a lot from him about the challenges at operation of the power grid. With that, Venkat, back to you. Floor is yours.
Great, thank you so much, Saeed, and thanks everyone for giving up an hour of your valuable time to come and listen to me speak. So appreciate the opportunity to talk about it, talk about this topic. The topic I kind of chose for this, and you can stop me in the middle, by the way, for any questions or hold it till the end, whatever you want. I do have a lot of slides, so I'll try to go through them in fairly short order as much as I can. Maybe skip a few if I'm running out of time, but essentially my topic today is to talk about challenges for electric power supply reliability and resiliency in a changing environment. And the reason I chose this topic is because while we talk about a lot of ways in which energy transition is taking place, the grid is evolving, one of the things to keep in mind is the imperative to still maintain reliable and resilient electricity. I mean, it is very important, and the thesis here is that it's becoming challenging and will likely become increasingly so if we don't take steps or processes to kind of make sure the reliability is still maintained. So with that kind of a background, I'm going to talk about I'm going to talk about a quick introduction to electric co-ops, in case for those who don't know about electric cooperatives, and about us, NRECA, and business and technology strategies. Talk a little bit about grid evolution. A lot of this you may be familiar with already. and then talk about some of the factors as I see it and impacting grid reliability, and talk about how are we going to look at power supply going forward with all the changes that are taking place, and then how do we want to plan and operate the grid to maintain reliability. Very quickly, co-ops are not-for-profit organizations. They were found in
I will.
start.
I think I'll just
Sorry.
print it off from here.
Oh, sorry. I heard somebody talk. So they are not-for-profit organizations. So there's about 900 of them across the country. 833 are distribution cooperatives, meaning they own and maintain distribution grids to serve power to consumers. They are primarily in the rural areas of the country, as opposed to cities or towns. They serve the rural population and serve 42 million consumers in the country. And yeah, as I said, they're not for profit. Think of them as HOAs, homeowners association organizations, similar to that structure, but providing electricity instead of maintaining a community or so on. So they are locally governed and member owned. They are owned by the community that serves them, as opposed to an investor owned utility, which looks at shareholders and things like that. They serve 13% of the US customers. They own 42% of the distribution lines across in the map that you can see the service area, service territory of all the electric cooperatives. And this kind of says two things. One is, you serve only 13% of consumers, but you own such a large portion of the country as service territory, meaning that there's less density of customers in the co-op service territories. That has implications in terms of operating and maintenance of the system. And also these rural areas, they contain a lot of what we call persistent poverty counties. Meaning that the people there are very susceptible to rate increases, cannot afford a lot of rate increases. So the co-ops have a very unique challenge of serving a very less dense area of not so well-off folks. So how do you do that, and how do you maintain reliability with all the changes that are taking place is a continuing challenge. For us, NRECA, National Rural Electric Cooperatives Association, we are the trade association for electric cooperatives. We do a typical thing a trade association does. We do advocacy, we do government relations and communication and so on. But we also do applied research, through our division called Business and Technology Strategies. We do look at pretty much the entire energy spectrum, planning and operating the grid, renewables, cybersecurity, resource adequacy, everything that's related to what our members do. And we do projects. We belong to organizations such as PCERC, for example, and take advantage of the research that's done. We work with vendors. In any way we can create tools and resources for our members to address challenge. And that's our mission. And then we kind of do that in a variety of channels. So the way we do it, we look at we have work groups. We look at pretty much every aspect of the spectrum. We have T&D, as you can see here, DERs, generation, bulk generation. We look at them. We look at data analytics, and we look at cyber and a bunch of other things. We also apply for federal grants through partnerships with universities such as yourselves and other organizations, and then kind of work on those projects and use the research results for our members' benefit. All right, so quickly moving to the state of the industry. The reason I wanted to highlight this is because it kind of gives a window into what the utilities are thinking. So this is from a Black & Veatch survey. Black & Veatch puts out the survey every year on it's what they call the electric report every year. This is from the 2023 one. The reason I wanted to highlight this is because how reliability and resiliency play into a lot of things that we see. This is from a survey of electric utilities across the country. Top 3 challenging issues. The answer was renewable integration was number 1. It was number 1 last year and still number 1 this year. And then aging infrastructure is the other one. There is supply chain constraints, and there is rate issues and cost issues and things like that. So again, and then environmental regulations. We know about the EPA rules that are being passed or proposed rather. On limiting carbon emissions. So how do you kind of reconcile that with the need for firm, reliable power when those coal and gas units and oil units retire? or get replaced. So so those are the top three. You can see all the other ones down the list there, but all of them have an implication on reliability and resiliency, and that's one of the main points of this kind of thinking among utility CEOs. A few other things, more than 80% of them in the left-hand chart there, they give resiliency more consideration when you plan and operate the grid. When you look at hurricanes and storms and snowstorms and everything else, that becomes one of the top of the mind issues when they plan and operate the grid. And then the new loads that are coming, data centers or other loads that are coming in, again has an impact on how do you continue to serve, create and serve reliable electricity, primarily for two reasons. We see from our members, from our utilities, the need for cleaner power, more renewable power. How do you make sure you still maintain reliability? And then, of course, on the infrastructure side, how do you look at load? For example, when a load keeps varying, it's much more varying and much more uncertain today than it was before, due to, for example, rooftop solar or energy storage coming in, making the load more and more unpredictable. So how do you really look at forecasting the load and then serving it in a reliable fashion there? And then again, what are the following drivers of grid modernization? Again, number one, renewable energy penetration, and then resiliency events, low probability, high frequency events such as natural hazards and others are some of the key drivers of grid modernization. Just a couple of more things. We talked about cold, ice, and I'm going to skip this. Cyber is the other key threat that we are seeing across the country, especially on smaller utilities such as electric co-ops who do not have the resources to withstand a cyber attack. That's a key driver of reliability. Because before, reliability used to mean high quality power and resilient power, but now it's cyber secure power is a huge issue now on reliability. And then unfortunately, physically secure power is also becoming a bigger issue, as was demonstrated by a few incidents across the country where people shot at substations or damaged otherwise infrastructure. So cyber and physical security is becoming a big issue when you look at maintaining reliable power. So that's kind of the state of the industry, looking at renewables, looking at aging infrastructure, and looking at low frequency, high impact events, and really preparing for it in addition to cybersecurity. Those are on top of mind of the utility folks across the utilities, no matter what kind of utility you are. So that's the kind of the state of the industry. I just want to transition into grid evolution a little bit. A lot of these you would be familiar with, but I think some of it bears repeating in the context of reliability. Looking at grid evolution to be more transactive, more dynamic, all the way from real-time load monitoring on the bottom left and all the way to transactive energy. As consumers, we see consumers installing more and more rooftop solar and energy storage and smart loads and so on, that their desire to transact on an individual basis, peer-to-peer basis, also increases. And so what we see is that from our members, from our consumers who are co-op serve, a lot of them want options to sell their solar or sell their energy storage power to their neighbor or to elsewhere and monetize that to the extent possible. So how do you enable that and still be in charge of reliable electricity, right? So those are some of the issues to face. So what we see again is a fundamental change in the way the grid is being operated for DER. It's one of our former chief scientists at NRECA. He called it, the previous grid was controlled through angular momentum. All it means is rotating machines. It was controlled by rotating machines. That's how frequency was maintained. Now you are now transitioning. We see that transition to what we call analytically driven control, electronically driven control, not inertial control or otherwise rotating machine control or angular momentum control. So that transition is pretty tough. You can have anecdotal or ad hoc control on some spots on the grid, but to move an entire grid from rotating angular momentum based or rotating machinery control to a complete electronic control, still maintain frequency and voltages and power transfer and so on, is not a solved problem yet. I'm not aware of a mathematical formulation that will still give that, based on the stuff you all are studying or all have studied on power systems. That's being changed as we go forward. So how do we really model that and understand that is still a problem that we have. On top of it, what else we see here on the grid evolution? We see a lot of technologies coming in. We see a role for data analytics quite a bit. How do you acquire data from the systems that you already have, such as meters or OMS or geographical information systems? And then how do you use them? How do you analyze and use them? That's a non-trivial problem simply because of the amount of data that's involved. The analytics is probably simpler, but acquiring that large amount of data, storing it and accessing it and cleaning it and validating it is a non-trivial problem that has a lot of attention in the industry. We also see IT-OT convergence from a cyber point of view, and also even from an operational point of view. There are very few grid technologies or utility systems that are not connected to the internet. Standalone systems used to be the way to have that firewall and separated, but no longer, simply because of the software updates that are needed, just because of the flexibility of access and monitoring and so on. So that poses a unique problem in terms of attack surfaces. Attack envelopes increased just because of the IT-OT convergence on the cyber threats that I mentioned before. We also see, on the positive side, we also see a lot of embedded technology use in operations. For example, we see linemen going with an iPad or with even an augmented reality glasses, being able to look at substations, digital version of the substations, and look at the actual substation and being able to map different equipment and kind of learn on the job and be able to operate on the job using that. So those kind of technologies are coming to play, and that's all good. I mean, it provides benefits, but we see that technology incursion in a much rapid fashion than it was before. And then increasingly we see attention being paid to ADMS. How do you bring all the previously separate utility systems, such as I mentioned before, GIS, outage management, DERMS, SCADA, and AMI? How do you bring them all together into an advanced distribution management system? How do you bring them all together, let them all talk to each other, and kind of the whole is greater than the sum of the parts type approach, and then being able to look at distribution system in a much more dynamic fashion and much more controllable fashion. So ADMS is getting a lot of attention in the utility space, and especially in the co-op space, and really looking at it and what are the benefits it can provide is something that is of interest quite a bit. Overall, we look at different grid technologies, core systems I just spoke about, all the different systems coming together. Digital asset management, a lot of interest in digital twins. For example, a digital twin of a substation, how can you create one, and what are truly the benefits of doing that? It's still unclear. It's a lot of information out there, but not a lot of validated cost benefit analysis of digital twin, but nevertheless, the digital asset management is a growing field. Robotics, I talked about augmented reality and drones. Drones are one of the fastest growing technologies in the West, especially among the co-ops for vegetation management, wildfire risk assessment, asset management, and so on. So we see a lot of interest on utilities co-ops adopting drones, and the challenge, of course, is when it comes to drones, data acquisition and storage. You quickly get a huge amount of data on images and videos. How do you take that and store it and access it? And then also, how do you do automated image recognition? That is something that we are working on to see if a drone goes and takes an image of image and or videos, can we use AI and machine learning to identify anomalies, identify first the asset and then the anomaly of that asset? Can we do that? That's a emerging field that's going on. and then a bunch, and then EVs, of course, as the other growth area that we see. How do we optimize a grid that has that can have EVs in it, that can have charging stations in it, and how do you still maintain the reliability? What kind of infrastructure is needed to maintain reliability? So those are some of the technologies that we see, and obviously there's a lot of growth in. I'm skipping a few slides here because I want to get to some more informative slides on reliability. But a huge growth area, we see that also in our co-ops, and then finally the unique thing about what we see in this growth is the grid edge growth. You got AMI, which is essentially it's no longer just a meter. We see it as a sensor of what's happening on the lower consumption point on the grid. But in terms of IoT, we see the distributed storage and EVs and distributed PV. All of that growth is happening on the grid edge. The question then is, how can it be visible to you? How can you monitor it, and then how can you control it? What infrastructure is needed and who's going to pay for it, really, for that infrastructure is a question that's still not solved yet. So we see that also quite a bit. And one of the things I always see, I'm sure you all have attended DistribuTech or IEEE, EST&D and others and gone to the expo there. We have our own annual meeting, NREC's annual meeting, and an expo every year. I see the ecosystem of companies that are coming in. It's changing over the past 5 years. You get a lot more smaller startups and the smaller companies that are getting into the utility technology space quite a bit, and it's only increasing. So there's a lot more technology options and technology choices than before. And there's a lot of IT companies, IT technology companies coming into the OT space and offering solutions. So we see that quite a bit. And a lot of our co-ops are looking at trying a lot of them out or already doing that. So that is the other thing we see on grid evolution. So I know I'm jumping topics, but again, please stop me if you have a question or a clarification. So what are the factors impacting grid reliability, at least as we see it from our co-op perspective and NREC's perspective, given all the grid evolution and given the state of the industry? So for that, when we think about reliability, there's a NERC definition of reliability. It's really three things. One is operational reliability, meaning that under steady state conditions, no natural hazards or anything, can you assure a high quality of power at the appropriate time and at the appropriate amount that it's needed, right? At the appropriate space, meaning that the location on the grid. So at the right location, right time, right amount, at the right quality in steady state. That's the operational reliability. This capacities, of course, for planning purposes, given your forecast going forward on how much power you would need, do you have the sufficient capacity to be able to support that power supply, right? That's from a resource adequacy perspective. The third part is a resiliency, meaning that under non-steady state conditions, when you have a natural hazard or a human-made hazard, how resilient is your system? How can you withstand it, and how can you adapt to it, and how can you recover from it? So reliability has these three components to it. So when I say reliability, I kind of mean all of these together, not just the operational reliability aspect, just to keep that in mind. So when you look at what are the things that affect either of these or all of these factors, right? Look at bulk power systems. On the bulk side, generation and transmission fuel availability is something we see, we feel. We all know about the winter storms, Winter Storm Uri and others, Elliott and others. What happened to natural gas availability, and therefore what happened to power supply as a result of that is one thing. The other thing I mentioned, what we call a NERC calls a disorderly retirement. When you have coal and gas plants retiring because they are uneconomic or forced by environmental constraints, the plan to replace them is not always there. So you just have a hole where the plant used to be, a big coal plant used to be, providing inertia, providing voltage support, providing frequency support, and providing a large amount of power. When you take that away, how do you deal with the loss of reliability that it will have unless you make arrangements for alternate power supply? So that's called disorderly retirement, meaning not planned sufficiently far in advance. So that's a big problem. Supply chain, as we all know, is a problem. Weather is something we cannot control, but nevertheless, it's an issue for resiliency. And I talked about cyber physical security. Permitting is another one. A transmission line, you'd be lucky if you get that built in 10 years, if not more. That's how hard permitting a new transmission line is. The higher the voltage, the longer it takes to build for a variety of reasons. I mean, won't go into that, but that's a huge issue for permitting. So if you plan for a lot of transmission to support reliability, count on it being there only in a couple of decades, not in a couple of years. So you got to plan for it accordingly. Anyway, so that's on the bulk side. On the distribution side, you have electrification as one of the key drivers of load growth, electrification of transportation, electrification of other anything that can be electrified in a beneficial manner is being electrified. So we see that as an increase in load. And then, of course, on top of transportation is the biggest increase in load due to electrification. Weather, again, all the other issues, DERs is a big issue for reliability. DERs should be properly used to maintain reliability, or it can cause an adverse impact on reliability. So that's something to think about. One of the things which is kind of, well, not surprising, but may not be that intuitive, is the business models that can cause an impact on reliability. If I have a declining load as a utility due to increase in solar or otherwise, but I'm still asked to maintain the reliability of the system in a manner comparable to what it was before, then what kind of business model do I pursue to make sure that I'm sustainable as an organization to be able to do that, make those investments? So if I'm not able to make those investments in upgrading infrastructure, then reliability is the casualty, right? So how do you incentivize properly by the right business models to maintain reliability? So those are some of the key overall factors. I'm going to go into maybe a little bit of detail on a few of those, but just want to give you kind of a picture of all the factors that need to be looked at when we talk about reliability and resiliency for the future of the grid. And then, of course, consumer expectations is a big one. If I'm a consumer, I have energy storage, I have solar, I have everything else, but I still count on the utility to give me reliable power. If I'm not usually, I mean, not the fault of anyone, but it's just that usually consumers are not very understanding about a loss of power. Even if the solar is not there or their energy storage is not there, they still want the utility to supply power. So how do I, as a utility, plan for that? To keep power in reserve, assuming all of their in-home energy sources fail, I need to supply the power. So how do I do that? Right. So that's another dimension to this. Anyway, so I mentioned electrification is a key driver. Transportation is number one. We see a lot of heat pumps coming in. The better version of heat pumps are coming in, which can operate in cold weather really well. More efficient, and HVAC and lighting and so on. A lot of the C&I, commercial and industrial customers, look at electrification as a way to reduce costs and be more cleaner. And a lot of different ways in which they can improve their operation. So we see electric boilers, electrification of process heating, and some of the agricultural and industrial equipment being electrified. So that has that, and then residential, of course, you got electric heating and smart thermostats and things like that. So it's a key driver of load growth and hence a challenge. And cyber, I already talked about it, so I'm going to skip it. We all know about the cyber impacts of that. The other thing, this from an Enroll study that was issued, I think, last year. The entire load curve is changing. When you look at and there's a reason for all of that, and those are all the different types of load that are listed here. But it's more of it's not energy growth anymore. It's not electricity energy growth. It's about demand growth, meaning that I want the load curve is becoming more spikier. I suppose. I mean, the ideal load for we all looked at power systems. The ideal load is a flat load, right? So you can easily plan for it and do it. A flat line, horizontal line. No, it's becoming more and more spikier. and more unpredictable. How do you really plan to serve that? I mean, that's shown by the change in load, as I mentioned before, due to electrification. For example, if you have EVs and if all of the folks come in and plug in their cars at 5 p.m. In the garage, you just got a spiky load that's coming in exactly during the time when solar starts ramping down due to sunset. So how do you handle that? Those kind of issues come up, and then being able to predict that and plan for that is an issue. So the second issue, or I don't know, some number of issues. It's the IBR, inverter-based resources. They are increasing pretty much every equipment that you have right now. It's a generation or storage or so on. It's all inverter-based. So that's becoming a bigger issue both at the distribution level and at a transmission level, and that's something that NERC is looking at. Some of you maybe, I'm sure, are familiar with it. It's not gone away. It's only increased. A few examples of we still need to. The point here is that we still need to understand really how inverters operate. How do they behave under different system conditions, under system steady state, system disturbances? How do they interact with one another, and how do they respond to signals caused by other equipment on the grid, and so on. So, a simple thing, I'm sure some of you may have heard of this, the two disturbances that happened in Texas, May 2021 and June 2022. You had, in each case, there was a fault, a single phase to ground fault, but then and then it cleared, but then you had a bunch of inverters tripping, 1,000 megawatts, more than that of solar generation tripped. And what are the reasons for tripping? You have a bunch of this table here from NERC shows that in each one, you can see the number of reasons for which how many megawatts tripped due to each reason and due to both disturbances. The key here is the last one. Voltages remained in the no trip zone of VRTs. The IEEE 1547 standard, they have the LVRT, low voltage right through. The voltages did not go beyond that, which means the inverter should not have tripped. That's the bottom line, but they did, and these are the reasons. So then this speaks to a couple of things. When you are counting on increasing amount of inverter-based generation to maintain power supply and reliability, and when you have situations like this, what do? Right? So you just banked on something that on power supply and they tripped, and you are no longer able to assure reliability. So those are some of the things that are still. ERCOT and NERC have done other steps after this to understand more, require more analyses and things like that. But nevertheless, this just highlights an issue on looking at inverter-based generation and their impact on reliability. That's on the bulk side, by the way, the one that I showed before. This is on the distribution side. What are some of the consequences of inverter-based resources? Biggest one is fault current, right? You all know that. It's a high impedance equipment, and therefore it's a low amount of fault current. It's not high enough to trip. It's not low as a steady state current. It's somewhere in between, which means if it's not tripped, loads are exposed to higher than normal currents, increase heating, and therefore can result in additional wear and tear without them being aware of the reason for it, right? So and then there's a whole issue of what are the impacts to transformers due to high currents from inverter-based generation, and then there's a lot of other things that are being learned right now. When you want to create an island just with batteries, how does it in terms of voltage performance, in terms of just load performance, what are some of the things to be aware of? So the point is we are still very much on a learning phase. When you look at inverter-based resources and their impact on loads and their impact on distribution grids, so that's an active field of research that needs to move to understand the impact on reliability. Protection systems is a whole different field. We have merely scratched the surface on that. How do you look at designing or reconfiguring protection systems, distribution protection systems for when you have a majority of inverter-based resources, either generation or loads? Most of the distribution protection is based on overcurrent relays, right? The simplest one, overcurrent relays. Well, if you don't have a high enough fault current, you just rendered that not very usable. So do you use distance relays, which are expensive? So how do you use that? So the trend is now look at some of the transmission protection systems and then trying to bring some of that principles back into distribution and do that, which means replacing reconfiguring relays, and who's going to pay for that? So that's an issue. But nevertheless, protection systems is a key issue that needs to be looked at. And this from a slide from Hawaii Electric, who are kind of the bleeding edge of this whole thing. So they're redoing their entire protection system to maintain reliability. The other one is that when you look at EV charging, what does that do to residential AC stalling? So basically, this is a well-known problem: fault-induced delayed voltage recovery. It's basically caused due to residential AC stalling, and basically the point here is that you need to have the right settings on your EV chargers. If not, it can make the problem worse. In terms of voltage recovery. If you have a EV plugged in charging during the fault occurs, the behavior of the inverters on the EV, EVs can make the problem worse. You can get into details of this, but essentially all this points to a need for looking at what settings you need on the inverters to make sure they are grid friendly and not grid unfriendly. And that's again an evolving research area. So yeah, and then finally, of course, the inertia. Assuming that's why I put this, assuming a 60 Hertz grid will still exist. I mean, we don't know that. I mean, it need not. There's no reason for the grid to be at 60 Hertz or 50 for that matter. You can have it at any frequency, but nevertheless, this shows inertia and ERCOT and how it's reduced over the years as more and more non-synchronous generation has come in. And then it's not under any raising of alarm bells yet. I mean, they have a inertia level of 100 gigawatt second. It's measured in gigawatt seconds, essentially how much gigawatts you need for each second. That's a synchronous generation. So you can see that it went from 132 gigawatt second down to 115 gigawatt second. So not yet at 100, which is the threshold, but it's decreasing. The other thing is the percent of load that's being served is also at a reduced inertia is also increasing. So you have two effects that are happening. The inertial threshold is decreasing. The percent of load served by a lower inertial threshold is also increasing. So at some point, there needs to be this needs to be looked at and see how we can kind of mitigate some of this effect, assuming we still have a 60 Hertz synchronous grid. And this, and again, ERCOT is kind of a unique case in an islanded system, essentially. So you have a pretty sensitive towards inertial fluctuations, but nevertheless something to look at. All right. So I think my final two topics here. I know I'm going a bit fast, but anyway. So what are the challenges as we talk about energy transition? Energy transition is a term, at least the way I explain it, or at least I look at it here, is moving from a carbon-heavy generation source to a non-carbon-heavy or cleaner generation source, and that's energy transition. So, but there are some challenges. A few of these we just talked about in terms of reliability and the inverter-based resources and so on. There's more. Okay. Not to rain on the energy transition, but just to kind of show that some of the real issues that are there that needs to be solved if we want to have an energy transition. The first one is the interconnection queue. Just look at this is the interconnection queues till 2022. Look at the last box here that says all regions. The last bar on the last box, 2022, it's about 2,000 gigawatts. This is in gigawatts, so 2 terawatts of generation in the interconnection queue. A lot of it is energy storage, either standalone or hybrid, solar and storage together, or solar standalone. So that accounts for probably about 75% of the 2 terawatts that's there. All of them, of course, are inverter-based generation. So think about that. If that comes in over the next any number of years, usually the success rate on this, or not success rate, the installation rate is about 20%. 1 in 5 gets installed. So 2 terawatts, that's 400 gigawatts, right? 400 gigawatts gets installed of inverter-based generation. What will that do to the system? That's something to look at. But also, there's a lot more transmission that's needed. If there are goals in the country for 80% renewable by 2030, 100% by 2035, something like that. It doesn't matter, 2030, 35, 40. The point is, not all of it is going to be distributed. A lot of it is going to be utility-based transmission, which means we need more transmission, not at the same place where the coal and gas was, in a different place. So we need more transmission, more interconnections, more permitting, more infrastructure. So that is something to think about when we think about replacing a large amount of existing generation with new, larger renewables. So how much transmission is needed? This was done DOE National Transmission Needs Study. The gap here, the gray is where it is right now. The green is what's needed. The green is where we need to be. So the gap represents the amount of transmission that's needed to get to 2035 with all the interconnection that we just saw. So you can see Midwest has the highest gap of transmission that's needed, Mid-Atlantic, and then Southeast and the Plains, and then of course Texas. They all need a lot of transmission to get to utilize the large amount of solar and wind if it gets built in the system. So the question is, as I mentioned before, transmission takes anywhere between 10 to 20 years to get built. So that's something to think about when we think about the energy transition. And so then this was a study from Midwest ISO. I like this a lot in terms of investigating innovative non-wired solutions. What can you do? You want to site closer to the load. You want to have other aspects of how do you get that generation to the load. You have a bunch of different alternatives. Still, the gray is transmission, but then the rest of it you do have others such as synchronous condensers, STATCOMs, and other technologies that will enable you to increase transfer capacity and kind of get more of that generation. So either way, this cost needs to be included in the energy transition. The other part is that if you have 80% renewables, you also need other generation to provide firm power and to have that as a backup, right? How do you get that? You get that through nuclear. Again, a lot of lead time. Vogtle was the latest one that came in Southern Territory. Took 20 years to build, and it's at least 3 times over the cost, if I'm not mistaken, probably more. So cost is huge. Carbon capture is still in the research phase with a high cost right now. So that's something that's going on. Hydrogen, we'll see what happens. Still a lot of problems to be solved on that. And then the rest of it is still very, very much, all of it is very much in the research stage or very expensive. So that's something to look at when we talk about that. And supply chain risk is real because we have a huge amount of demand on the EV side, plus a huge amount of demand on the stationary storage, the hybrid and the solar plus storage side. So you're going to have we need 20 times more nickel and 40 times more lithium in the next 20 years. Because most of the batteries are lithium-ion batteries right now, we don't have a viable alternative that's already scaled and installed. So we need to have diversity in battery chemistry. That's another thing you're looking at. And then there's a lot more lithium mines that are needed. Somebody was saying, we are trading in oil wells, but for these big lithium mines to get the battery. So which one do you want? So that's something. I know I have probably 9 minutes remaining. So very quickly, so what does the future of electricity look like? Given all that we talked about, energy transition and so on, we see the members, consumers wanting more, essentially, going from a ratepayer and a consumer to what we call, I'm sure you heard the term prosumers and transumers, not just having control of their consumption, but being able to trade electricity, sell and buy electricity in a very granular fashion, which the grids weren't designed for. None of the electric grids were designed to do what the consumers, some of the consumers at least, want to do. So how do we handle that? The other thing we are seeing is the virtual power plants. Every distributed generation, DER, that's installed is capable of being aggregated into a virtual power plant and being bid on the market based on FERC Order 2222 and then in the general proclivity of kind of trying to take advantage of the asset that the consumer already has. This is the Generac alone, just the company Generac behind the meter assets. You got 2 million home standby generators, batteries, thermostat, C&I. The question is, this is a huge opportunity here, how to aggregate it and offer it into the market for sale. And then that's one of the futures of electricity supply coming in. And then, of course, transactive energy, I talked about it quite a bit. Just one of the things, the bottom chart here shows New Hampshire Electric Co-op in New Hampshire. They send this price signal out. So you can actually sell electricity based on this price signal. If you have a battery or a solar, they get paid based on this price signal. So the question from a consumer is optimizing their energy supply, energy generation to optimize their earnings, minimize their electricity bill and optimize their earnings. From a utility perspective, when they send out this price curve, how do they anticipate a response and how do they plan for it? For reliability still is another thing to think about, but essentially transactive is there. And then, yeah, distribution reliability through price signals. This is being piloted quite a bit. So if you have, for example, a EV, and then you want to plug it in, can you get paid for not plugging it in to reduce the load on a distribution transformer and then plug it in later? How do you price signals to spur action on the consumer who are not used to these kind of price signals? How do you do that, and how do you get the effect? Kind of a transactive energy in practice, so to speak. Anyway, I'll skip this in the interest of time. So planning and operating the future grid. So we see a lot of interdependence in the markets. I just mentioned about gas and electric interdependence. It's being increased. We also see obviously a lot of interdependence. Usually consumption and distribution stood alone, passive, but no longer. There's backfeed issues into the transmission system. Consumption is playing a more active part. So how do you really model all of them together and then model the effects of one has on the other in terms of planning and operating the grid? And then what are the business models that are needed to actualize that? A distribution system operator, just like a transmission system operator, is the future role of a distribution utility. You just operate the grid and let the generators and loads transact with each other in the kind of a more extreme model. So how do you ensure reliability in that scenario? And then of course I talked about smart inverters. And then the other thing is, given the load generation and load uncertainties, what do you do for maintaining the distribution grid assets? How do you forecast the loading on the asset? And then how do you forecast the wear and tear on the asset? And then how do you do an asset replacement plan when the factors that are causing the asset loading are not in your control? How do you really do an asset replacement plan, and how do you plan for it? This is something that a lot of our members are seeing. Transformers reaching the end of life much faster than what was predicted, and similar things for other distribution assets that are going on. So resource planning, I'd rather go here. Integrated. So this is some of you may have heard the term integrated distributed resource planning. Previously, before FERC order 1992, NOPR, this is how it was done. The utilities were vertically integrated, and then they did the entire generation, transmission, distribution planning together. Utilities got separated. Generation, transmission became one entity, and then distribution was another. So now there's a need for everybody to come back together again in planning because of DER. What impact DER has upstream, and then what impact this changes in power supply, bulk power supply has downstream. So there's a lot of need for information exchanged across the verticals, so to speak, generation, transmission, distribution, and then and consumption, and then plan on a more integrated fashion. Taking into account, for example, the value of DER and relieving overloads up on the bulk transmission system that may defer transmission upgrades or anything else. So how do you really look at this kind of an integrated distributed resource planning framework and be able to kind of have input, broad input in every aspect of the planning in the utility is something that we are looking into. DOE is looking into that. NARUC is looking at a lot of entities are looking into this IDRP concept and looking at how to implement that. Let's see what else. Future technologies, data analytics, I mentioned quite a bit. A lot of data is coming at the utilities. The resources are woefully inadequate for workforce related, how to look at data analytics. So that is a need that we see. Understanding the consumers better is another one that we see quite a bit. How do you look at that? How do you use data from AMI or from other utility systems? Sorry, I'm going through a few of these at the end. I'll send you the presentation later. Home energy management. How do you do that? How do you do autonomous home energy management, which can respond to price signals? We have a few pilot projects for some other co-ops looking at it. And then the meters, the meters, is that the end of the traditional meters as we know it? Because a cell phone is a meter now. A EV charger is a meter. A Amazon Echo or a thermostat is a meter, right? So the standard electricity meter, it's much more than that anymore. Any sensor can be a meter, and that we see that quite a bit in technology advancement. So how do you really look at a granular view of load consumption in each house, and then how do you really address that? Finally, generative AI. We see that coming in. You all know about ChatGPT and what it did. Essentially, it's growing quite a bit, and we see applications of that coming in every aspect of the utility space. I think that's all I have. I went through quite a bit very fast. Oh, also we are hiring, so please go to electric.coop and look at job postings. We have some positions. So if any of you looking for a job. All right, Saeed, I'm going back to you.
That was very informative talk, so we really appreciate that. So let's take the questions. So maybe first we go to the people online. So if anybody has a question, please unmute yourself and ask your question. I see Brent has posted the question. Brent, can you unmute yourself and ask the question directly from? For this
Sure.
Today?
I'll try. Can you hear me okay?
Oh, yeah.
So. Okay, thanks very much. I work a lot with co-ops here in Washington, Oregon, Idaho, primarily on the protection and substation side. And I've run into a lot of challenges. You mentioned IBRs and protection. And I've run into a lot of issues with the unique nature of some of the co-op loads out here. We have 12 kV and 24/9 kV circuits that feed primarily irrigation for agriculture. And so these circuits, some of these circuits are literally 12 to 15 megawatts, 24 hours a day, 7 days a week, nonstop in the summer. And then there's zero during the winter. Like they go months without going above, say, 500 kW. And so trying to tie in 5, 10 megawatt solar projects to these circuits becomes really challenging. Is NRECA looking at those types of IBR on irrigation type circuits that have those seasonal load differences? Can you point me to any references or work that's being done on that?
Well, we are not specifically looking at this. I've heard of the similar situation where you have these large solar and low load, essentially, right? So, and at least seasonally, in other areas too, in Colorado and in North Carolina, similarly, that's really the issue there, the variation in irrigation load. But to answer your question, no, we do not have something readily available. I would also encourage you to look at EPRI, who did a lot of analysis on the reconfiguring protection with this situation. And I can also reach out to a couple of co-ops I know to see how they solve this problem in Colorado, and then maybe get back to you. But no, I don't have anything ready on this specific issue.
Okay, thanks. Yeah, I appreciate your presentation. I do think the whole co-op entity is unique, like you were saying, on so many levels. And I find it very enjoyable to work with co-ops, but obviously some real engineering challenges here and there. Thank you.
Yeah, sure. And one thing I do want to mention is that thanks, Brent. Appreciate that. One of the pilot projects we did was what are the settings for smart inverters on long rural feeders, similar to the one that you mentioned. And one of the things we worked with a co-op in White River called White River in Colorado, where they had a 10 megawatt solar at the end of a long rural feeder with very light load. And then the question is, how do you really look at smart inverter settings on there? What settings do you need to have for smart inverters? So that's an ongoing project that we want to do more rural feeders and look at smart inverters and see what settings would really help that system. So not directly related to protection, but definitely would feed into that.
No, that's perfect. That's exactly the kind of thing I'm running into out here too. So,
okay.
Thank you.
Thank you, Brent. So Anil, could you please go ahead and ask your question? Yeah, please.
Thank you, Venkat. Great presentation. Yesterday, this morning, I was reading on LinkedIn that Portugal has been 100% renewable resources for the last 6 days. When do you see that happening in the continental US?
If you look at ERCOT instantaneous penetration, they post the instantaneous penetration every day, and I think they went to 60%, if I'm not mistaken, something like that, 50, 60%, and they were doing well. So and Ireland also, I think, went to pretty close to 100 or that. So it's possible. There's a difference between instantaneous penetration and steady state penetration, for lack of a better term, right? So that those are the things I think. And also, honestly, I mean, everything is fine until it's not. So that's when the issue comes in, or else. As I said, there's really nothing stopping us from no need to have a 60 hertz grid. There's really nothing stopping us theoretically.
Thank you, Anil, for your question. So anybody else online want to ask question from Dr. Venkat? No? Okay, so then how about you guys? So anybody want to go ahead and ask question? Usually you have questions. Go ahead.
Okay. So I actually have one. So my question is on the FIDVR that you talked on. So because I did some simulation in my lab with the real-time simulations tool, and I realized that when we have some level of IBR generation in the system, the FIDVR is like there's a faster recovery of voltage after the fault, and when there is no IBR generation at all, it's a bit worse. So, but it also makes sense that we realize the importance of having a rotational generation in the system. So in the future grid where everything is just IBR, like what's the state of the FIDVR? Like, what is it going to look like if we don't have anything rotating in the system? And like, how do we understand, or what would be the state of this voltage recovery after fault?
Good question. Good question for you to do continued research. I don't have the answer for that. It's what I at least I've heard is that I'm sure you're familiar with the term synthetic inertia, right? So again, I have my own views on what it really means as what it really is, but the question really is, should you or can you mimic using the inverters the behavior of rotational machines in terms of a droop or in terms of whatever else you want to do? And if so, if you want to do that, because to your earlier point, inverters actually, when set properly, can provide a lot of benefit in terms of recovery. voltage recovery, they can be much faster. I mean, as long as you don't go start oscillating back and forth like this, right? You kind of need to damp it down also. But years back in the Western wind and solar integration studies and part 3 and things like that, it was found that given the proper setting of the inverters, it was much better at recovering from disturbances than even a rotating machine should. So all this means, and it goes back to my earlier point on understanding the inverter behaviors better. That becomes really key. I mean, honestly, we need more studies and more research on that. Understanding inverters, not one inverter, a family of inverters. I'll even forget the manufacturer differences for now because they are also significant, but let's keep that aside for now. Just even from the same manufacturer, if you have a high penetration, say, let's say, I'm just picking a number, 50% inverter penetration across a given area, how do they respond, in terms of disturbances or even under steady state operation voltage control? Do they fight with each other in terms of settings? How do you let them coordinate different? Those are all not solved issues at all. And this is just grid following. Grid farming is a whole different aspect, okay, of how do you have grid farming inverters transition from a grid following mode to a grid farming mode, when and how do you maintain it? Those are all very, very research fields right now, no matter what you may see in the news or you may see there. Those are not solved yet. So very, very good research problems in my mind to focus on. Yeah, I'm sorry, I don't have a better answer for you, but don't have it.
Thank you. Other question? No lucky person? Oh, you have.
You mentioned that inverters have some behaviors that cannot be predicted. For example, when there was a fault in Texas, some of the inverters trip and some of them cut from the system. So my answer is it the same as we have it in the simulations? For example, if we simulate the fault in our simulator, do we get the same results, or in the real life it is different, so we cannot predict what will happen when the faults happen?
Very, very good question. Good. That point was looked at in the report. By the way, I highly recommend you read this. All of you read this report. That you can easily find it online. Very well written report and very informative. And yes, it has to do with a couple of things. First is the answer to your question is maybe. Sorry. Some can be duplicated, some could not be, and that was the whole point of that was pointed out in one of the reports. Second, the reason for that is due to the accuracy of the inverter models. Okay, so all of these are different manufacturer models, and getting the right model for an inverter, sometimes it may seem trivial, but it's not. That has an effect on simulation, the results that you get while simulating it. So ERCOT tried to do so. What ERCOT did was, after the first disturbance, the 2021 one, they did those simulations, and then they were able to avoid some of the reasons during the second time, avoid the tripping for some of the reasons. But then they found a bunch of new reasons for which the inverters tripped the second time. Okay, so for example, in this, right, inverter instantaneous AC over current, none tripped, but 459 tripped on the second one, right? Inverter DC bus voltage unbalance, none tripped, but 211 megawatts tripped. And you can see vice versa ones also. Phase lock loop of loss of synchronism, 389 megawatts tripped, but did not trip on the other ones because they were able to, based on simulations, change those settings. So it's not all understood yet, and that's really the point. And one of the things that came out of these two, one of the things that came disturbance is the requirement for the manufacturers to submit verified models, not just the initial models, the template models, but actually field tested models. And there is proprietariness to it, and there's all kinds of aspects to it. But nevertheless, I think that became a requirement after these two disturbances, I think. So.
In the last question,
So we're having a problem when we increase the number of inverter-based resources because we lose our inertia, right? And earlier in the presentation, you said that the ideal load is flat, but we're getting more spiky, which that spikiness is the reason why we would want more inertia, I think. And so instead of looking at ways to increase the inertia per se of the grid or more of the stability, have we ever looked at increasing the controllability of loads? And so, because right now we all consider ourselves essential, we all want power all the time. So have we looked at incentivizing people building controllable loads so that if the utility decides we can trip them can regulate them just to flatten the load, because then we don't need inertia if we have a truly flat load?
Yeah, no, well, first of all, on the demand management side, to your point on controllable loads, it's been there for decades now. Our member co-ops and others have looked at water heater control and things like that to reduce demand charges, not to reduce the spikiness. Well, to reduce the spikiness because of demand charges, and the controllability of loads have increased due to technology. So there's a lot of options for it. And yes, that in fact. That is one of the underutilized means for controlling inertia, unfortunately. So, and because of the reason that you just mentioned, we all consider ourselves essential. We want the load when we want it, right? That behavior and that perception needs to change a little bit. It's changed in places like California already. In other regions of the country, it may change, whatever. So there's a lot of aspects to it. In terms of inertia, there is again, you can imagine a zero inertia system and still be reliable if you have the right controls. But one thing I think as a counter to that is that think about electricity is the only commodity whose speed of controls is equal to the commodity speed, right? Electricity travels at the same speed as the electronic controls. So we don't have any other commodity. So at some point, the latency in controls will be a detriment, or the speed of electricity will be much faster. The change there will be much faster than we can control it. And that is one of the reasons for the research on inverters, 50% inverter penetration. Can you control and maintain the stable grid, right? So yeah, I agree with you on demand management. Absolutely, a very untapped field there. So.
Thank you.
Okay, so we already have taken your time more than. I have one question I couldn't resist. So let me ask you. So I really like the idea of this when you talked about integration and distribution system and so on and so forth. So usually in literature, we see two types of management. One series of books, they talk about the kind of co-simulation of transmission and distribution system. And some people talk about kind of going to the virtual power plant type of thing. So basically you assume the whole distribution system is one virtual power plant and assign some regulation for that one. So therefore we don't need to worry about that one, how this operates. So what is your take from industry point of view? Which one do you think would be more appropriate approach, or what do you see for that?
Well, it depends on how much changes. If your distribution system is pretty static, then yeah, you model it as a single point load delivery point and then do that's what's being done. But as distribution system gets more and more load becomes more and more time varying and more DER comes in, there is increasing value to model the distribution system more explicitly in my mind, because you uncover value streams that you would not otherwise be able to do if you just lump it all into a VPP or some other approximation. I think there's a lot of, and there are other policy aspects to that with the FERC order 2222 and so on. A simple example is that if I create a VPP on my own in the distribution grid and bid it into the wholesale market, can the distribution operator have a kind of a right to recall, so to speak, if they want to maintain distribution reliability? They won't even know about it if you lump it unless you model it granular, right? So those kind of things, I think, may have a need for modeling more granular. So that's my take on it.
Okay, I really appreciate that. That was very informative talk. So we really appreciate that. Maybe one more talk.
Thank you for the opportunity, and thank you for all the questions.
Oh, thank you, and hopefully see. Are you attending next week?
I'll be there. Yeah.
Okay, so see you then. So I'll see you then. Okay,
So
thank you.
thanks all.
Okay,
Bye.
bye. Bye. Thank you.